Evening. My name is Robert. Welcome to lesson 3. Our topic that we're going to discuss and look on today, it's on load versus no load conditions of a transformer. Okay, that's what we're going to be focusing on today. So I made a short summary of the overview, as you can see on the top right, on the top left. Okay, I made that. So without any waste of time, let us first look at the first case. Okay, let us look at the offload condition of a transformer, how a transformer behaves when there is no load connected in the secondary side of the winding. I will draw a simple sketch of the simplest representation of a transformer. Okay, so you have your core, you have your first winding or your input winding or your primary winding, and then you have your secondary winding. Okay, so this is your supply. Okay, and then you'll have your current I1. So this is no load. So when there is no load connected in the secondary side, okay, this is secondary side. Secondary side. This is primary. Okay, sorry about that. When there is no load connected on the secondary side, let us look at what happens. Okay, let us look at what happens. On your primary, your AC supply, when it supplies the primary winding, the principle of electricity says that whenever a current flows through a conductor, there will be a field surrounding that current. Okay, so I1, there will be a field around it, around the current that will flow inside the first winding. Okay, so we see that this coil or this winding has a certain number of turns. Okay, so the current will flow through those number of turns. Okay, and then we know that we have your F1 is equals to I1 times N1. So when the current I1 flows through the number of turns, it causes an existence of a magnetomotive force. Okay, so I like calling this F1 or this magnetomotive force a magnetic supply. That's what I like calling it. Okay, it acts like a supply for the magnetic circuit. Okay, so when this happens, there'll be an MMF. Okay, so the wireless field around the winding will cause some magnetic particles. Okay, the core has certain magnetic particles that we call the magnetic domains. Magnetic domains. These are core particles. Okay, these are core particles. So this wireless field of the current, when the current passes through a certain number of turns, will cause the magnetic domains to change position. Okay, they'll change position. So the moment they change their their initial position, flux will start to flow, okay, inside the core. Flux will start to flow, okay. So we usually assume the flux to always flow clockwise, okay. We always assume it to flow clockwise. So when the flux flows inside the core, what happens is that the field becomes stronger, okay. The field around the winding becomes stronger, and then not all of the flux goes inside the core. Some of the flux is lost, so it'll move that way, some of the flux. So we call it leakage flux. We call it leakage flux because it is leaking. It is leaking. It's called leakage flux, okay. So not all of the flux goes inside the core, okay. But irrespective of that is that we know that what will happen is that this flux will have a change in nature because it was caused by AC, so it is changing, okay. So as this flux changes, it will cut the same winding that has caused it, which is the primary winding. It will cut the primary winding, okay. It will cut the primary winding. So when it cuts the primary winding, what happens is that an EMF is induced, which is called E1, okay. So an EMF is induced. This happens according to the principle of electromagnetic induction, okay. According to the principle of electromagnetic induction, when the flux cuts the primary winding, there'll be E1. So there'll be E1. E1 will exist inside the across the windings, okay. An EMF is induced. So what does the principle of electromagnetic induction say? What does it say? Okay, electromagnetic induction, what does it say? It says that a changing flux cuts a stationary conductor at right angles. And EMF is induced. This EMF that is induced will be equal with V1 in magnitude but opposite in direction. It will be opposite in direction to it, okay. So a flux that is changing cuts a stationary conductor, okay, or we can have a situation whereby things are the other way around, whereby the flux is stationary and the conductor is moving, okay. So in this case, the conductor is stationary and then the flux is moving because it is changing, okay. So when this happens, an EMF is induced which will be equal to the supply voltage, okay, in magnitude, but it will be opposite in direction to it. All right, this means that E1 is equals to V1 in magnitude, but they're opposite in direction, okay. They're opposite in direction to each other. opposite direction. Okay, opposite direction. All right, they're opposite in direction. Okay, that is the principle of operation of a transformer. Okay, all right, so now you have E1, you have the flux that is flowing inside the core. This is V1. Okay, and then you have I1, and then there's a field around it. So V1 and E1, they are opposite in direction. Okay, so remember, when this flux cuts the winding that was responsible for its existence, we call this self-inductance. Self-inductance. It is called self-inductance. Why? Because the same flux that was caused by the same winding cuts the same winding. So it is called self-inductance. Self-inductance. Okay. So now we know that the flux is flowing that way. It's flowing that way inside the core, clockwise direction. Okay. So now when the flux keeps flowing that way, it also cuts the second winding. So when it cuts the second winding, the same principle of electromagnetic induction is being obeyed. Okay, meaning when this flux, let me call it the original flux, flux 1. Okay, when this flux 1 cuts the second winding, an EMF is also induced, which is called E2. Okay, E2 will be in the same direction, as E1. They're in the same direction. Okay, same direction. They're in the same direction. So as they're in the same direction, the both of them are opposite to V1. Okay, so that is what happens. All right. So right now we know that when E2 exists across winding 2, okay, it will cause a current to flow inside the second winding, which is called I2. I2 will start to flow because of E2. Okay. However, remember, this is open. The winding is open. Okay. So because the winding is open, it means it's an open circuit. So in this case, I2 will be 0 amperes. 0 ampere. 0. Alright. I2 is 0. Alright. So as short as it is, this is the condition that happens when your transformer is operating on no load. Okay. And also remember, because the flux 1 is cutting the second winding, which was not responsible for its existence, in this case it is not called self-inductance. In this case we call it mutual inductance. Mutual inductance. Okay, it is called mutual inductance. Alright, so this is what happens on the no load operation of a transformer. This is what happens, okay, on no load. Alright, so I would like us to move on to the second case. The second case, we are gonna look on the condition of on load. Okay, on load condition of a transformer. We're gonna look at how a transformer behaves when it is on load. Okay, what happens when a transformer has a load connected on its secondary side? So here you have your AC, you have V1, you have I1. This is your flux. Okay, I would like to make that bigger. Okay, I'd like to make it bigger. All right. All right. Perfect. V1, I1, flux 1, clockwise direction. You have a second winding. However, this time you have a load, Z load. Okay. All right. So I'm gonna start on the primary side and explain the same thing that I explained. All right. The current flowing in the primary side, or the principle simply says that whenever a current flows through a conductor, there's a field surrounding it. So that current flows through a number of turns, and then it will cause a flux 1 to be available inside the core. Okay, and then flux 1 cuts the first winding, and then when it cuts the first winding, it induces an EMF. We call it E1. Okay, E1 is equal in magnitude but opposite in direction to V1. Okay, all right, and then that is called self-inductance. All right. Okay, so the same flux flows in a clockwise direction, and then it cuts the second winding. So when it cuts the second winding, it induces a second EMF, which is called E2. It induces E2. Okay, so E2, because it's induced across the second winding, it will cause a current to flow inside that winding, which is called I2. I2. All right. Remember, in the first case, I2 was 0 because the secondary side was open. There was no load. Okay, but in this case, now we have a load. My question is, what will happen now? All right, let's find out. All right, remember the principle goes even is obeyed even on the secondary side. I2 also has a field around it, so I2 will flow through the loop. It will flow through the loop, then flow through the loop, and then this I2 will go through the number of turns in the secondary. It will also flow through the number of turns in the secondary. All right. So the moment it flows through a number of turns, what causes or what happens is that I2 will cause F2. There will be F2, which is called F2 is equals to I2 N2. Okay, so this is the second magnetomotive force. All right, caused due to I2. All right, so what basically happens is that I2 does the same thing that I1 did. All right, so I2 flows through the number of turns, and then it causes F2, which is I2 times N2, and then this F2 will cause a second flux inside the core. Okay, let's call this flux 2. All right, so the difference between flux 2 and flux 1 is that they are opposite in direction. So flux 2 will oppose flux 1. Okay, but they are not equal in magnitude. Flux 2 will be less. Okay, so this opposition of flux 2 will cause flux 2 causes flux 1 to decrease. Okay, to decrease to a certain extent. All right, so flux 1 will decrease, will drop. Okay, not drop to 0. It won't drop to 0, but it will be reduced to a certain extent because of flux 2. All right, so now what happens when flux 1 decreases? to a certain extent, what happens? What happens is that E1 will also decrease to a certain extent. Okay. Remember, the reason flux 1, the reason E1 is decreasing is because flux 1 is decreasing, and flux 1 has caused E1 to be available. Okay, so E1 is dependent on flux 1. That's why E1 decreases, because flux 1 is decreasing. Okay, so they will both decrease to a certain extent. All right, so now what happens next when this happens? Okay, when this happens, or what happens? The principle says, okay, the rule says V1 is balanced with E1. Okay, why? Because they're opposite and equal. Okay, the rule says that V1 is balanced with E1 because they're opposite in direction and they're equal in magnitude. All right, so the decrease of E1, the decrease of E1 will trigger V1 to come up with a way to compensate or to cover up for the decrease, so that it can correct the decrease that has happened, so that it still wants to balance with E1. So it wants to correct, okay, it wants to correct that decrease so that it can cover up for it. But how does it do that? How does V1 react to that? How will V1 react to that? Okay, so V1 will try and compensate for the decrease of E1 by releasing more current in the primary. Okay, so V1 will try and compensate for the decrease of E1 by releasing more current in the primary winding. Okay, I'll explain this. All right, I'll explain this. All right. Remember, each and every side of the transformer has a capacity. Okay, has rated voltage and rated current. For example, let's say I full load or rated for the primary side. Okay, let's say it is I'm just giving an example. Okay, I'm just giving an example. Let's say rated current for this side it's 20 amp. Okay, let's say it's 20 amp. I'm just giving an example. All right. Okay, obviously V1 is always V full load. Okay, and then that's I. All right. What this means is that for V1 to release more current, it will release an extra current. Maybe this extra current will be 10 amps, for example. Okay, meaning the total current that will flow will no more be 20, it will be 30 amp. Okay, let me write it properly. Let's assume that previously the current that was flowing in the primary was 20 amps, and then when the process goes on, you have E1 decreases, and then it causes V1 to release more current. So that more current, let's assume it is 10 amps on top of the 20 amps. So the total current that will flow in the primary will be 30 amps. It will be a combination of the two. So this means what? This means overload. Okay, because it is above rated current. Okay, so it is above rated current. Rated current is 20 amps. So now you'll realize that because of what's happening, because of the decrease of E1, V1 is released an extra 10 amps. So the current that's flowing is 30 amps now. It's above the rated. All right. So this is how V1 tries to compensate. Okay, it tries to compensate for this. So usually this current that is flowing extra, that is extra in the primary, we call it additional current. We call it additional current. Okay, or simply I prime 2. We call it I prime 2. All right, we call it I prime 2. It is also called the mirror image, so the mirror current. Mirror current of I2. I like calling this way. It's the mirror current of I2. Okay. All right. It is the mirror current of I2. Okay. So when this current flows in the primary, you'll have an F3. F3. Okay. Remember we had we have original, it's F1, I1, N1. Okay. And then we have F2, I2, N2. So now we have F3. F3 is I prime 2 times N1 because it is in the primary. Okay, it is in the primary. So now what will happen is that inside this core, a third flux shall be present. This was flux 1, clockwise, flux 2, anti-clockwise. Okay, now we know that inside this winding there's also I prime 2, which is the additional current that V1 has released to try and correct the reduction that happened. Okay, so F3 will cause a third flux, flux 3. So this flux 3, okay, because it is the mirror image of flux 2, meaning it will oppose flux 2, and then it will flow clockwise also. It will flow clockwise. Okay, flux 3 will flow clockwise. So you realize that flux 1 and flux 3 are in the same direction. Okay, and flux 2 is equal to flux 3 minus flux 3. Why? Because minus for the direction, they're opposite in direction, but they're equal in magnitude. Flux 2 and flux 3. All right. So when this happens, what happens? Okay, because this flux 3 is a result of I prime 2, the additional current, going through the number of primary turns and then causing flux 3. Okay, so we know that this additional current I prime 2, it is the mirror image of flux 2, so it is equal in magnitude but opposite in direction to flux 2. So they try and do what? They try and cancel up. Okay, so they try and cancel up. They try and cancel up. Okay, so I'm gonna say V1 releases extra current. I prime 2 to cause flux 3 which is equal okay. V1 releases extra current I prime 2 to cause flux 3 which is equal in magnitude to flux 2. Okay, these two will cancel. And the result is that flux 1 will increase. Flux 1 will then increase to its original value. Okay. When flux 2 and flux 3 cancel, flux 1 will increase to its original value. So if flux 1 increases to its original value, what happens is that E1 increases also to its original value. All right. E1 will also increase to its original value because flux 1 has also been restored. Okay, flux 2 and flux 3 cancel each other, and then flux 1 increases to its original value, and then it causes E1 to also increase to its original value. When this happens, it means that therefore E1 will again be balanced. With V1. Okay, E1 will again be balanced with V1, so they'll now be balanced. So okay, so now you know that in a transformer, in the conditions whereby the secondary winding is closed, V1 and E1 always want to be balanced with each other. The V1 does not like the reduction of E1 because it will cause it to release more current. They always have to be balanced. They always have to be balanced. Okay, so this is what happens. This is what happens on the load condition of a transformer. Basically, after everything happens, after flux 2 cancels with flux 1, everything returns back to normal. Okay, so I would like you to understand and to know that flux 2 and flux 3, the cancellation of these two fluxes does not take place immediately. Okay, it can take hours. Okay, it is slow in reality than it is in theory. Right now, when I say that flux 2 and flux 3 will cancel, maybe someone thinks they will cancel immediately. No, in reality it takes hours. It can even take days. Okay, it can take a day. I don't know, a day, but it does not cancel immediately. It takes hours. All right. Okay, it takes hours. It takes time. They cancel each other at a slower rate. Okay, and then obviously when they cancel each other, what happens? The current I prime 2 will also decrease, and then the current will return back to the rated current. Okay, meaning I prime 2 will drop and I1 will be full load. All right, so this is what also happens. All right. Okay, so I would like to additionally explain something. Okay, I would basically like to explain something. All right. A transformer has equivalent circuits. A transformer has equivalent circuits. Okay, so these equivalent circuits, there are three kinds. Okay, there's exact equivalent circuit. That's exact equivalent. Okay, so in the exact equivalent you have this is Z1, then you have something like this. Okay, you have something like this. This is E2, this is E1. This part we call it ideal. It is ideal because if you consider this portion of the circuit, there is no resistance. It is perfect transformer. Okay, so we call it ideal, the ideal part. So this is V1. Okay, supply. The current that will pass through Z1, we call it I1. Okay, and then on this branch you have RC, you have XU. Okay, and then the current that will go to this branch, we call it IO. Okay, and then the current that moves to the third branch, we call it I prime 2. Exactly what I was explaining about. Okay, and then IO, when it gets in this branches, it divides, and then one part we call it IC. Okay, and then the other current that flows on the other branch, we call it IU. All right. Okay, we call it IU. We call it IU. All right. So this is what we call the exact equivalent circuit. It's the representation of an equivalent circuit of a transformer. Okay. So there are three ways we can represent how a transformer, the relationship of the parameters, how is the relationship inside the transformer for all the parameters with each other. All right. So you can see that I prime 2 is flowing. This is the primary winding. This is secondary. So you realize that I prime 2 is flowing the primary. Okay, that's why we're saying I prime 2 is a mirror image of I2. Okay, it is the mirror image of I2. Alright, just that I haven't drawn it properly. Okay, I haven't drawn it properly. Okay, so let me make another drawing. Okay, I want to make something clear. Okay, you have this part. Okay, I prime 2 flows here. So if you take if you take this part is what we call the load part. Okay, or the load circuit. Load circuit. Okay, and then this part is what we call supply circuit. Okay, the last part, which is the branch, this branch that has RC and XU, this is what we call core or magnetic circuit. Okay, so you can see that these are three different things. Okay, this is very much helpful for you to understand in some problems when you solve, because sometimes you meet an equation that says I2 over I1 is equals to KT. Okay, I don't have a problem with this equation. Okay, but I know that I2, it's I2 on the secondary side. The current that will flow here is I2. Okay, and then I1, I know that is the current that flows here. Alright, so now what happens if you meet another equation, because they're both valid? I2 over I prime 2 is equals to KT. Alright, this is the second equation. Okay, it's the second equation. The I2 is the same I2. Okay, but what is I prime 2? Can I say I prime 2 is the same as I1? Nope, I'm wrong. This is where sometimes it gets confusing in some calculations. So you have to understand that I2 over I prime 2 is the current here. Okay, so when you're using this equation, okay, I like calling the equation of the load equation. Load equation of KT. I like calling that. Why? Because this is the load current in the secondary, so it's I2 full load, and then this is I prime 2, which is I full load 1. I prime 2 or I full load 1. Okay, I prime 2 or I full load 1. So I2 is what, or I full load 2. So I'm trying to explain this because sometimes it's confusing when you calculate. So you have to understand that these two equations is not the same thing. Alright, it's not the same thing. Okay, alright. So having explained that, I'm not done. I would like to explain further. Okay. I would like to explain further. I'm going to continue breaking down these equivalent circuits for you. So I want it to make sense. Okay. So remember now I told you the magnetic circuit, and then I told you the supply circuit, I told you the load circuit. Okay, which is the mirror image of the secondary side. Okay. So I also told you that I1 and I'2 is not the same thing. Okay. So we have this circuit which is called the equivalent circuit. The equivalent circuit. This is the exact equivalent circuit of a transformer. We say it is exact because if you check, the magnetic circuit has been placed after, represented and placed after Z1. So if this magnetic circuit is placed after Z1 across this winding, we say it is exact. Okay, so now there's another second circuit whereby they realize that if we leave the circuit connected like this, this circuit is complicated. So to make it easy, we can take the magnetic branch and place it before Z1. So if we do that, it will be easy to analyze this circuit. So because it will be easy to analyze this circuit, there will be a certain error that is introduced in doing this. So that error, it's small, it is negligible. The error or the deviation of doing so, it is negligible. So having explained that, if they do that, it gives rise to a second circuit, which is a simplified circuit, which is called the approximate equivalent circuit. Sorry, it is called the approximate exact. Okay, approximate exact equivalent circuit. Okay, so this is the second circuit. Okay, the second circuit. So it is this way. It is this way. So you have RC XU, and then this is Z1, then this is, it's like this. RC XU IO IC IU E1 E2. Alright, so now you see that this magnetic circuit, it has been placed before Z1. Okay, just by doing that, we call this circuit the approximate exact equivalent circuit. Okay, so like I said, there's an error in doing that, but the error is negligible. The deviation of doing that is negligible. Okay, so this is the second circuit that is simplified. The first circuit was being simplified to the second circuit, which is called the approximate equivalent circuit. These circuits are some things that you should keep in mind, because we're gonna focus more on using this circuit when we're dealing with open and short circuit test. They're very much important. Okay, so this is the second representation of the circuit. All right, so now they also realize that remember the magnetic circuit. What happens in the magnetic circuit? You get the ion losses. Okay, ion losses are found in the magnetic circuit. Okay, ion losses are found in the magnetic circuit. And then what happens? Copper losses found in the windings. Okay, these two, P ion and P copper, are called major losses of a transformer. Okay, they are called major losses of a transformer. So now ion losses are dependent on rated voltage. Okay, ion losses are dependent on rated voltage of the side in which we connect our lines to supply. Okay, remember, just that I'm going to teach more on this when I'm doing open and short circuit test, but when we test ion losses, we open the high voltage side, we leave it open, and then we supply the low voltage side. Okay, so in that case, our ion losses are dependent on the rated voltage of the low voltage side, the side in which we supply. So ion losses are dependent on rated voltage. You need the total 100% of V1. You need 100% of V1 to determine the ion losses, total rated. All right. So the copper losses are dependent on rated current in the windings. Okay, copper losses are dependent on rated current in the windings, meaning we perform copper losses under full load conditions. All right, so this is the difference between the two. They are the major losses, they are the biggest losses in a transformer, but the ion losses are dependent on the total voltage, and then the copper losses are dependent on the total current. And then when we test copper losses, we short circuit the low voltage side, and then we supply the high voltage side. So this means it will be dependent on the rated current on the side in which you connected. Okay, don't worry, I'm going to explain more about this properly when I'm releasing my video on open and short circuit test. I'll repeat the same information. Okay, it's just that I'm explaining this to try and explain something. So that's why I'm explaining this, because I'm going to explain something next. All right. Okay. So now we need to move to the third circuit. Okay, third circuit, which is called the approximate equivalent circuit. It's called the approximate equivalent circuit. So now what they say, okay, what the rule says, they say that for us to get the third circuit, we consider the fact that since the ion losses are dependent on rated voltage, okay, the rated voltage in such a condition, we assume that the rated voltage in a short circuit test, it's 10%. Okay, 10% of the rated voltage circulates full load current on the other side of the winding, okay, under short circuit conditions. So we say, because if we are to perform a short circuit test, the voltage is 10% of the full load voltage. So we assume that the ion losses are neglected, because since ion losses depend on the rated voltage, 10% is too small to make the ion losses to be of any significance. Okay, so for us to obtain the third test, we have to explain the conditions based on the short circuit test. Okay, and another thing also, it's not only that, it's because it's like we use these two conditions. Okay, the rated voltage under short circuit test is 10%, is too small, meaning like if we include it in such a condition to try and obtain the third circuit, it means that 10% of the voltage, of the total rated voltage, will be available, and then the ion losses will be too small to be neglected. So if they're too small to be neglected, we will assume that the magnetic branch does not exist. Okay, that's the first condition. The second condition, we also assume that the no load current, it's 6% of the full load current. Okay, no load current, IO no load, is very small. Three to 6% of full load. Okay, because of this, we neglect the magnetic circuit. All right, so you can see that in this circuit, if we neglect the magnetic circuit, the circuit breaks down to this. It's gonna look like this. It's gonna look like this. It's gonna look like this. Okay, so the third circuit is going to look like this. This is the simplest circuit because there's no magnetic branch. This is what we call approximate equivalent circuit. Okay, this is the third kind of circuit that you're gonna meet. All right, so these are the three kinds of circuits, and then this is how we got to derive to making their existence. This is what the theory says. Okay, this is how the theory derives these kinds of circuits. Okay, so in this case, I1 will be equals to I1 will be approximately equals to I prime 2. So in this case, if you have I2 over I1 is equals to KT, is the same thing as I prime I2. It's the same thing as I2 It's the same thing as I2 over I prime 2 is equals to KT. Same thing in this case. In this case, the same thing, doesn't matter. Okay. All right. So I hope everything I explained makes sense. I hope so. I thank whoever took their time to support me and to watch until the end. I thank you so much. We've come to the end of our lesson. Take care. God bless you. And please subscribe to my channel. Please like. Please share. I really appreciate that. It means a lot. Thank you so much. Thank you. Take care.